Okay, so doing the surface integral means two surface integrals added together because it's a closed surface. We've got the top lid, that's a disk, and then the cone. Let's draw it, first of all. Okay, so we'll call the cone S1 and the disk S2, and the total flux will be the sum of the S1 flux integral and the S2 flux integral. So S1 first. What does it mean to do this? So the flux is going to be the double integral over S1 of F what, dot RU cross RV dA, right? du dV. This is our ds vector, right? Which we just talked about. It's that vector that's orthogonal to the surface, has the value of the area of one element. That's basically the parallelogram, right? The cross product gives the parallelogram area and vector orthogonal to it. It's just what we want. So what are we going to choose for u and v? Then we need to figure out how we're going to parameterize this cone in u and v. What are our u and v going to be? Yeah, probably r and theta is going to be good, right? R and theta is going to be good for this because not only is it a cone, but the projection of that cone is a disk. So r and theta this time, right? We saw before a circular one, but we were projecting it over square. So we said x and y, do with x and y. But here, when we do that double integral, it'll be over the disk in the xy plane. So we want to do r and theta. So that means that we need to parameterize so r comma theta. We need to get the x, y, and z components in r and theta. So x is r cosine theta. Here's my abbreviations again. R sine theta and so what is the z coordinate on the cone? R, right? Z is r because z is square root of x squared plus y squared. And then we got to do our cross product. So we got ijk. And we're going to do r partial with respect to r, the partial with respect to theta. Partial with respect to r is cos theta, sine theta, and 1. With respect to theta, negative r sine theta, r cosine theta, and 0. Gives us cross product of 0, negative r cos theta. J is negative r sine theta. And k is, let's see, r cosine squared plus r sine squared, all equals r. So I'm going kind of fast because you should have lots practice web work with lots of these, but please stop me if I lose you on something. Okay, so let's think about this. We want outward orientation. So when you have outward orientation on this part of the surface, the cone, what does that look like? So what does outward orientation look like? What will those vectors be like? Yeah, they're going to kind of pointing angle down, right? Orthogonal to the surface. So does our cross product agree with that?
No.
Because? Right, look, the z values are positive, but our outward orientation shows that those vectors are pointing down. That means to get the outward orientation, we really should have done r theta cross our r. Right, we should have flipped these. And if we do that, what do we get? So for outward orientation, yeah, just everything is just going to flip the signs. negative r. And now those vectors will point down and out and agree with outward orientation rather than what we did. And so we would have gotten that if we had done our theta cross our r. Okay, did you guys get your question answered? You guys are good? Yeah, okay. All right, so then we're going to write our f in terms of our parameterization and do the dot product. So here we go. It's going to be the double integral. F is going to be, what's y? R sine theta. Negative r cosine theta. And z is r dot. We're going to use this one then, right? Because we want outward, so r cos theta, r sine theta, and negative r. Now the question is it dr d theta or r dr d theta? Yeah, so if you look at what's going on here, it's f dot the cross product du dv. So it should just be dr d theta. But if you look at the cross product, what do you notice in the cross product? They all have an r. So there's the r, right? So the r for the polar coordinates is in the cross product. So the only time that you're going to use r dr d theta is if it's like you're switching. Like your dA is originally in a rectangular and you're switching to polar. Then the dx dy is equivalent to r dr d theta. But here, since we started from the beginning with r and theta, we're not making a switch into polar coordinates. It's just truly you're just going to follow your nose here, follow exactly what it says, dr d theta, and then we recognize that the r for the r d theta, r dr d theta, is in the cross product. It's in every component. Yeah?
So if we were to do it in Cartesian up until this point and we want to switch to polar, then we would add the r dr.
Right, so if you wrote this whole thing in x and y, you get it as a double integral in x and y, and then you decided you wanted to switch it. Then you would have to switch your dx dy to r dr d theta.
Okay.
But here, that's not necessary. Okay, so moving right along here, and then so what are our bounds? R goes from 0 to, I think z equals r, right? So when we get to z equals 4, z equals r, we also get to r equals 4. So 0 to 4 and 0 to 2 pi. Okay, and for time's sake, I think we can do this. You do the dot product, you do your double integral. So for time's sake, I'm just going to write down the final answer, which is negative 128 pi over 3. Is that fair? You know how to do the dot product, and then now you've got a double integral in terms of r and theta, and there's nothing too involved there. So is that the flux through the closed surface? Nope. It's not, because we need to also do S2. So S2. And what do you see about S2? Yep. So what does that mean? Yeah, we can use that other, instead of, we can avoid the whole cross product part of this, and we can do this way. Do F dot N ds. And that'll make our life a little bit easier. So what is N for outward orientation? This would be 0, 0, 1, right? That's nice. Okay, and so then F. So now we're in what? We're in Cartesian coordinates, right? We're in Cartesian coordinates. So F is going to be, we'll just write it as it is. Y, negative x, z, dot 0, 0, 1. And then we can project that thing into the xy plane. So over the projection of S2 into the xy plane, well, we'll just call that what we call regions before D, so D2. So d2 is the projection of the disk into the xy plane. All right, but what is z? We're in this disk. So z is always 4, right? So z is always 4, so we can that's 4 for every point where we're integrating. So this thing equals double integral of 4. And how are we going to solve this one? So now here's where, so we got dx dy, and we want to, our projection is the disk, so we definitely want to switch to polar. So here's where dx dy equals r dr d theta. So we get the integral 4r dr d theta. R goes from 0 to 4, 0 to 2 pi, and then for that's a super easy double integral, and then that's equal to 192 pi over 3. Please. Yeah.
For the first one,
Yeah.
why wouldn't the first integral be 0 to z or 0 to r?
It should be. Let's see.
Because those have the same limits.
Yeah, they do, because they're both, when we project both of those into the xy plane, we get the exact same projection. So the limits will be the same.
Okay.
Yeah, so it should be 0 to 4. You're right. It should be, we're right. Yeah, you get the same projection, and the limits are always about the projection into the plane. So since you get the same projection, you get the same limits. That's a good observation. Okay, this one turns out to be 192 pi over 3. And then when we add together, so then the total flux outward, can I call that total outflux, is negative 128 pi over 3 plus 192 pi over 3 equals 64 pi over 3. Is that right? Okay. Please ask. I went fast, so please ask. Yeah.
I'm missing how you got the, when you integrate 4r with respect to r, you get 2r squared, right?
Right.
And then you plug in 16 times 2 is 32.
Okay.
And then you integrate out with respect to theta, you get 32 theta.
I'm just going off last year.
That's 64 pi, right?
64 pi, right?
And then you multiply by 3.
Why do you multiply by 3?
Because you can have the same denominator, so you can just add them.
Oh, wait, yeah.
Is it right?
It's the same.
I'm just going off the last semester. I didn't think through that.
Yeah, it's the
Is it
same.
good?
Yeah.
Okay. Other questions, please ask. Yes, please.
So just to clarify, when on the second surface, the plane for the disk, I'm sorry, we set it up with the F times N and then ds,
Mm-hmm.
and because that's all in dx dy, we wanted to change the polar.
Yep.
And make it ordinary.
Yep.
Okay, when you set up the integral in polar,
So we chose u and v to be r and theta. So we're just going to follow this. There's no extra u or v in there, right? So if you start with r and theta and you follow through this, so it's going to be dr d theta, and then the r is there. It's part of the cross product because it's in every component of the cross product. Other questions? Okay, so we're going to talk about something called flux density. Flux density, let's talk about that. So we've been talking all about flux. So what is flux density? So flux density is the rate of change of flow of a vector field out from a given point in the field. So here's what describes that. So make sure you're not just copying words, but your brain is on. You're listening, okay? So flux density at a point P. We're going to look at the ratio of the flux of a small surface around P divided by the volume inside that surface. So that's where the density comes in. Right? So imagine you got a point P, and you're going to take a small surface around, closed surface around P. The flux out of that surface divided by the volume of what's inside that surface is flux density. Then we look at that ratio as the volume, as that surface shrinks around to the point. So that volume goes to 0. So flux density is flux per volume, right? It's flux per volume, but then as things shrink around P. So what would that be? So mathematically, we know our flux is a surface integral, f dot ds, and then over the volume inside S, but then it's that ratio as you crunch in on the point. What does that ratio become? Does the concept make sense? Yeah.
What is the volume inside of us? What is that talking about?
Well, S is a closed surface, right? S is a closed surface around P, so there's a volume inside. If it's a closed surface, then it's creating a solid, right? If it's a closed surface that's closed up, so then there's a solid involved. It's the volume of that solid. Other questions? Okay, so here's this is kind of a nice simple example that kind of defines what's happening here. So consider the vector field XYZ at the origin, and then let your S be a sphere of radius A. So that looks like this. So we've got a sphere of radius A is my little closed surface, and the origin is the point P. So what would, when you have the vector field, if the vector field is x, y, z, right, then for any sphere that you pick, what is and say we said the sphere has radius A. What's the magnitude of all the vectors on the sphere? All the vectors of the vector field at the sphere, what would the magnitude of those vectors be?
0.
It would also be A, right? Because if you're just taking the coordinates of x, y, z on the sphere, well, then the vector starting there, being the vector x, y, z, is just going to be have the same magnitude as the radius of the sphere, A. So we say the magnitude of f equals A. That's equals, not less than. Okay, so if we calculate the flux, then we've really got this like a constant, right? We have a constant magnitude of f on that whole sphere. So we don't have to integrate to find the flux. We can just multiply, right? How do we define flux? Flux is was just f dot s, right? Since f is constant, then we can just find the surface area of the sphere and just multiply by f, because it's constant over the whole area, right? Or in other words, what is cosine? What's cosine? What is theta? What is the angle between s vectors and f vectors? Yeah, because theta equals 0, right? That's all these force vectors of the field are in the exact same direction as s. So we can just simply multiply the magnitude of f times the magnitude of s. So the magnitude of f is A. Magnitude of s is? What's the magnitude of s? 4 pi r squared. That's what that says right there. Oh, yeah, so there it is, 4 pi r squared. Therefore, the flux is 4 pi a cubed. Surface area of the sphere. Since we have constant f vector on the whole surface, we don't have to do the integral. We can just simply do f times s. And cosine and theta is 0. So we get the flux is 4 pi a cubed. And then so flux density, we're going to do what? Divide by the volume. So we got 4 pi a cubed as our flux, divide by the volume, which is 4/3 pi a cubed, which is just 3, and so it doesn't matter what the volume is, right? No matter what the volume is, we get 3. So that means the flux density at the origin, or the rate of change of flow out from the origin, it has a magnitude of 3. Any observations? Anything this brings to mind, this discussion? When I first introduced the definition of flux density, flow out from a given point. Did that conjure anything? Yeah. No, it doesn't mean it's speeding up. Yeah.
Is it kind of like the rate of change?
Okay. Yeah.
Derivative?
Yeah. Yeah. Rate of change of the vector field. Derivative of the vector field. Which one? Remember, vector fields have 2 types of derivatives or rates of change. Curl and divergence. This would seem to be like divergence, right? Rate of change out from a point, like tendency of expansion or contraction. So what do you notice? We got 3. What's the divergence of f? 3, right? Because you take the partials with respect to each. The divergence of f is px plus qy plus rz is 3. So this idea of flux density is the same as divergence. That's not a proof, but that's just kind of showing that it is. So flux density is divergence. That's what flux density is, it's divergence. We just didn't frame it this way before, as flux per volume. This is not a proof. So I'm going to kind of walk through the proof in the next slide. Just give an outline of it. It's not too bad, it's not too hard. But questions on this example, or flux density? So flux density is divergence. Okay, so given a solid E with a boundary S, a closed boundary S, and a vector field F, we're going to look at one element, like a dV element. So the box volume is delta V. It's delta X by delta Y by delta Z, and then there's some like P, Q, and R at the point. But then across delta X and delta Y and delta Z, there could be a slight change. There could be a slight change in the vector of the vector field. And so we'll just look at the change across delta X. And I actually should have drawn this. Here, I got orange here. Oh, it's the perfect shade too. I'm going to draw white. That's kind of that's a better depiction there. Okay, so across delta x on this little box, there could be a change in the p vector, right? So the p vector, the p component of the vector is in the x direction, and so across delta x of the box, you could have a change in p. So this is like this is p x naught. So maybe this one back here is the p x naught y naught z naught, and then this one is p of x naught plus delta x y naught z naught. So there's a change in p as you change a little bit in x. So the flux density, what was flux density? It was flux per volume, right? Flux per volume. So the flux through the cube around x naught, y naught, z naught divided by the volume of the cube. So flux, what is flux? It's the force, the vector times area, right? So we got three components of that. So I'm looking at the x component. So it's going to be the area, delta y, delta z, times the change in p. So the change in this orange vector through, so times delta y, delta z would be the flux, that component of the flux. And then you have similar component of the flux in the y direction and in the z direction. And that all over the volume of the cube. So that's the flux density. And notice what happens when you separate out these fractions. This, what happens here. Delta y and delta z go away. See that? And you have the change in p per change in x. Well, what's that? That's the derivative of p with respect to x. And then the same thing happens with the other two. So you end up getting the change in p per change in x plus change in q per change in y plus change in r per change in z, which we know is the divergence formula. So this is more along the lines of the proof, kind of a skeleton of the proof, that the divergence, the flux density is the same as divergence. Now, since flux density essentially equals flux per volume, I can solve for the flux. If I solve for the flux, what do I get? Yeah, flux density times volume. So that's an important conclusion here. So the flux out of one box, is the flux density times the volume, but we just showed the flux density is divergence, right? So the flux out of one box, you can write as divergence of F times delta V. And we're going to use that, so we're about to use that. That's why I'm showing you that. So this slide shows that flux density and divergence are the same thing. And from that, we can say that the flux out of one little element is the divergence of F, i.e. flux density, times the little volume. Questions on that slide? So this brings us to the divergence theorem. The divergence theorem is we're going to sum up all the flux out of the little delta V boxes. And so we've seen this principle before. So we've got all these little adjacent elements inside of E. And what would happen if we summed up individually, calculated the flux out of all those boxes? What would happen? Yeah, we get the flux through the whole thing, but then what would happen as we did that? It's not liking me here. To do one box, we'd have to look at all surfaces, right? Yeah, so any adjacent, when you do that, so I'm going to do all the surfaces on that first one, then all the surfaces on the second one are going to be equal and opposite for adjacent faces. And so those fluxes will cancel out. So when you add them all up, the flux out of all the delta V boxes will sum up to what? The flux out of the outside surface, right? Because those are the only ones left that don't have a canceling effect. That was actually part 2. Part 1 is just use the result from the previous page. We're summing up all the flux out of the boxes. Well, flux is flux density times delta V, or divergence times delta V. So that's it. That's just looking at all of them individually and just adding them all up, all the flux out of all the boxes. And then part 2 is what you guys just said. So what you get is if you do surface integrals of all the boxes, and you get the cancellation effect of all, and then it's the same as what the surface integral of the outside of the whole volume E. Yes, sir.
So what about the fluxes that point inwards, like the inner surface?
What's that?
Like what about the so like in the 3D cube, we have both the fluxes that point out of the cube, like out of the board and then into the board, right?
Well, there's only one flux through that surface, and then whether it's the sign of it just depends if you choose inward or outward orientation. Is that what you're getting at? Are you getting at the fact that there's like an outside shell and then there's like the inside of the shell?
No, like just like all the like if you had a cube, like the one facing, you'll have a flux with the one facing at you and the one that's facing away from you, right?
I'm not getting your question. Ask me after class. Let's talk about it after class. So we can add up all the flux of the individual boxes. That's the first one up there. Or to do those fluxes, we can do the surface integrals of all the individual ones, and we get all the cancellation effect, and then we end up with the surface integral of the whole outside of that thing, which is surface integral of capital S. So then these two are equal. So summing up all the individual boxes means a triple integral of the divergence of F, and then doing the surface integral of the outside surface is our common flux integral. So these two are equal. And this is the divergence theorem. So if E is a solid with a piecewise smooth boundary S, and if F is a smooth vector field defined everywhere, then those two things are equal. Summing flux, summing up, so this is flux, like element by element, cube by cube throughout the whole solid is the same as doing the surface integral of the shell of it. You get the same result. How are F and divergence of F related? What is the divergence of F related to F? It's the form of a derivative, right? So divergence of F is like rate of change of F, right? And S is, so this is derivative, right? And what is S? S is boundary of E. So what do we have? You recognize this? Summing up all the little, accumulating all the flux element by element using the derivative or the rate of change is equivalent to finding the total change at the boundary. Remember what that is? What's that? That's another fundamental theorem. This is another fundamental theorem. It's looking at, this is a lot more disguised, but it still has all the same principles. Using the rate to accumulate flux bit by bit throughout the whole solid is the same as just finding the total flux out of at the boundary. So this is our third one. We had the fundamental theorem of line integrals. What was our second one? Remember what our second fundamental theorem was? Green's theorem. And here's our third one, divergence theorem. Okay, so let's go back and look at the problem we did, the surface integral we did at the beginning of class. Remember this? We're finding the surface integral of the flux out through this thing. You have a new perspective on this now? Yeah.
And just have
Of what? The triple integral of?
the divergence. And then your dx dy dz.
By that, this fits the bill for the divergence theorem because you're calculating the flux of a closed surface. So we can also calculate the triple integral of the divergence of f by what we just said. So who would have thought a triple integral would have been easier, right? The triple integral is easier. What's the divergence of f? Zero, 1. So 0 plus 0 plus 1. dv. How we want to solve that? The triple integral? We're going to use rectangular coordinates. Cylindrical coordinates, right? Cylindrical coordinates, which is r dz dr d theta. Z goes from 0 to 4.
Oh, sorry, no. It's
What's
not
the bottom?
the column. So R. So
0 is not the bottom of this, guys.
R.
0 is not the bottom. The bottom is the cone. So it's going to go from r to 4. And then r goes from 0 to 4, 0 to 2 to pi. And then we don't have time to solve it, but this, then you get, what should we get? 64 pi over 3, just like we got before when we did the surface integral in 2 parts. What a great way to start your weekend. If you have any questions, just I'll stick around if you have any questions. So you have a web work due tonight at 7, is it? And then I'll post another one for the weekend. And then I'll post written homework, okay? Put a lot of time into this. It's hard.
So this is very similar to like the fundamental line integrals. It's just another dimension. For line integrals, like so like the area was equal to like the outside.
Green's theorem, you mean?
Or Green's theorem, yeah, sorry.
Yeah, so Green's theorem was,
You had like a surface, and then you could integrate the outside lines of it, or
yeah,
you could
over
integrate the whole area.
dqx minus py dA equals the circulation over the boundary f dot dr. So now we got the triple integral over E of the divergence of f dv equals, yeah, there's all kinds of parallels here.
But it's gone through the same way of just kind of getting all of the insides kind of canceling out when you get to a small enough.
Yeah, so that would be the insides canceling out is this part over here.
Yeah.
So with Green's theorem, we were looking at little circulation integrals for all the elements, and that meant doing the circulation integral, and then all the
sides that were
all the common sides were equal and opposite to the one next to them, and so then we end up getting just all around the boundary.
Yeah.
That's this. Same thing here. So when we total up the flux for each little box, each little surface integral inside, the adjacent sides cancel, and then we get the whole outer boundary. Yep.
Yeah. Okay.